Let's switch immediately to Mariusz. Mariusz, the floor is yours now.
Sure.
Okay, our next topic is new equivariant dimensions, another work package, and Mariusz Tobolski is a new work package leader because Ludwik Dąbrowski, who was in charge of it, unfortunately soon he will retire, but he's still a big help in all that stuff. So now Mariusz will relate about the progress in this area. Go ahead, Mariusz.
Thank you very much. First of all, I'm very, very sorry for the confusion that I wasted everybody's time. I had some technical difficulties, some other issues. However, let me start and not waste any more of your time. So the work package here is called new equivariant dimensions, and the dimensions we want to talk are, of course, of algebras, and the algebras we are all interested in are graph algebras. So the full title should be new equivariant dimensions of graph algebras, of graph C-star algebras, higher rank graph algebras, and stuff like that. And I want to talk about the results, the state of the art, what we know about equivariant
Sorry,
dimensions.
Mariusz, could you switch the camera on? We are being recorded, and it's not nice to listen to someone whom you don't see.
Yeah, no problem. Okay, can you see me now?
Yeah, thanks.
Okay. So I will be talking about new equivariant dimension of graph C-star algebras, and this concept of dimension and the name dimension. This is something very, I don't know, very popular nowadays with classification of C-star algebras program. There are various dimensions: nuclear dimension, Rocklin dimension. So for PR reasons, we are also calling dimension what we're going to talk about. However, it's related mostly to the notion of a principal bundle, and principal bundles are related both are pivotal both in mathematics and physics, and we try to find an equivalent in this world of C-star algebras of a notion of a principal bundle. And graph algebras are such a nice class of examples that it's a great place to check your definition, your new notion of a principal bundle. And to start, I want to talk about principal bundles, but I'm going to start with freeness. So I'm going to first talk about freeness of actions. So this is all about dynamics. So there will always be an action of a, and in my setting, for the sake of this talk, the group will be compact abelian. And in the setting of graph algebras, it will even be, I will be even more specific. I'll talk about the U1 group and its finite subgroups. So this is the setting. I have a action of a compact abelian group on a unital C-star algebra. And this action gives rise to a grading by the dual group. So this is the Pontryagin dual of G, right? And this is how we define spectral subspaces of your algebra. So, so these are elements of the algebra such that after acting with G, you get the evaluation of the character on the specific element G, right? And we also use notation that the unit, the spectral subspace is a to the power G, which is the fixed point subalgebra, right? Because if we get a unit, we get alpha of G, alpha G of A equals A, which means that we're talking about fixed point subalgebra of your algebra A. And then Riefel in 1990, I think, defined the notion of freeness. So looking at actions on spaces, there's a notion of a free action of a group on a space. And now if we think about C-star algebras as non-commutative analogs of spaces via Gelfand-Naimark duality, we want to look at various analogs of freeness in the world of C-star algebras. And of course, there are many notions. One of them is the notion of a free action or saturated action by Riefel. And in the compact case, many of those other analogs of freeness agree. So let me focus on the Riefel definition. Now, this is a very simple definition, It just tells you that if you look at the spectral subspace A chi and you multiply it with A chi star, what you ask for is that the unit is in this subspace. This is something that is called in the world of algebra strong grading, right? Because we have a grading and we talk about strong grading. I'll be talking about strong grading in a second also. Right, so this is the definition of REFO. And as I mentioned before, if our C-star algebra is the algebra of continuous functions on some compact Hausdorff space, then freeness of the G action on A is equivalent to freeness of the induced action of G on X. Right, so this is how you relate freeness of actions of groups on spaces to the saturated or free action of a compact abelian group on a C-star algebra. Of course, let me only mention that for the sake of this talk, I'm talking about compact abelian groups, but there's a notion of saturated action for non-abelian groups or even quantum groups, compact quantum groups. And so this is pretty general. Okay. And this is our starting point, because classically we know that if we have a principal bundle in any sense you like, because in non-commutative geometry, usually you think about free and proper actions. Let's say everything, all space is compact. Or if you think about local triviality, it always implies that you have freeness. So it implies freeness. Any type of a notion that you think of when you have principal bundles, you want to have free actions. Now, this is a definition that we proposed with Eusebio Gardella, Piotr Hayec, and Jinchao of local triviality dimension. So I mentioned that sometimes in the world of non-commutative geometry, non-commutative topology, we talk about principal bundles as having free and proper actions. What I want to talk about here is something more. I want somehow unrelated to properness. So I want to have a free action and I want local triviality of my bundle. And this is the definition that we propose. First, some notation. So I have a compact group acting on a unital C-star algebra, and T is the identity function here. So you can think about this T as a generator of this non-unital C-star algebra. And now if n is the minimal non-negative integer such that we have G equivariant star homomorphisms, and we start counting from 0, and this is just a convention, from row 0 to row n, from this algebra, which is the cone algebra, right? So the cone algebra, so we have the C01 tensor C of G, and I don't specify the tensor product here because everything is commutative, and I land in my algebra A, and this map has to be G equivariant with respect to what actions. So there's an action on A that we define, that we start with, and then the action on this space is trivial on this part, and the action by right multiplication on G that induces an action of C on C of G. So we have those maps, and if they satisfy the following condition, so first we look at the image of the element, the special element T tensor 1, and we add all those elements. If this is invertible, we say that A has a weak local triviality dimension n. Okay, and we denote this by dim WLT. So this is the first definition where this sum is invertible. If it's equal to 1, we have the local triviality dimension or plain local triviality dimension. Next, if this sum is equal to 1 and also images of those row i's pairwise commute, then we talk about strong local triviality dimension. And it's easy to see that we're adding more and more assumptions. For 3, so 3 implies 2, 2 implies 1, right? So if strong local triviality dimension is finite, then the plain local triviality dimension is finite, then the weak local triviality dimension is finite. So we have the following implications. And let me mention, so I mentioned that this is, the idea here is to generalize the notion of a principal bundle, of a compact principal bundle from topology to C-star algebras. And there were many other definitions where you could think about instead of because we want to somehow capture the notion of an open cover here. And those maps row 0 to row n are supposed to play the role of the open cover, and those particular elements, we should think about them as the partition of unity functions for this cover. Okay, and because we want to think about open covers, and it's very hard to talk about open sets in non-commutative topology, so instead we talk about partitions of unity, right? That's those maps row 0 up to row n. If you think about closed covers, and that's what was done before this definition, which is from 2018, was if you think about closed covers, you get a different notion that's called piecewise triviality. And even classically, if you think here about, let's say, closed covers, already classically, there are some examples of piecewise trivial bundles that are not locally trivial, because you can always go from local triviality to piecewise triviality, because you have your partition of unity, and you just look at the closed supports of your partition of unity functions. So that's the definition. It's
but it's worth mentioning that you cannot go the other way around.
Oh yes, of course. Thank you. Yeah, this is what I was trying to get at, is that there is an example of a piecewise trivial bundle that is not locally trivial, and this example comes from work of Piotr Polbaum, I think Wojtek Szymański and Rainer Mattes, where they talk about non-commutative geometry approach to principal bundles, and there's this example of bubble space that is piecewise trivial but not locally trivial. Okay, so now let me, so this is the definition, and that's the idea is that it was an open problem to even find a candidate for a definition for a locally trivial principal bundle that would include local triviality on an open cover, because open sets are very hard to describe in C-star algebra language. There's the notion of open projections, which is connected, and but even there it's difficult to have a very definite answer of what an open set is. So instead we talk about partition of unity functions, and we have this definition which seems to work very well in a lot of examples. And now the idea of this work package and of this part of the project is to check this definition on graph C-star algebras, on high rank graph C-star algebras, or on, I don't know, quantum graph algebras, and all those examples, and see which of them are locally trivial, give you locally trivial principal bundles in this sense.
Maybe let me just remark very briefly that the reason why we have these three different flavors is not because we try to randomly explore all possible generalities, but because real life examples enforce on us that in some circumstances one definition works properly, and another situation, in another setting, another definition works properly. You know, the goal of abstract tools is that they work in examples, that you can solve something using these tools. And that's the reason for so many flavors, okay?
Yeah, thank you very much. I was going to mention this, and I'll show you examples where one of the dimensions work nice and the other one not so nice, and so on. So yeah, thank you for, this is exactly true, and I will show you examples of different flavors where some of the dimensions are useful and some of them are not as useful, let's say. So we have examples when one of the dimensions would be infinite, but let's say infinite local triviality dimension, but finite weak local triviality dimension, or infinite strong local triviality dimension, but still finite local triviality and stuff like that. Okay. So let me go to I want to mention first the classical picture is that, again, if our algebra is the algebra of functions on some compact Hausdorff space, then first of all the local triviality dimensions are equal. So each of those definitions generalize local triviality of principal bundles. But like it usually happens in the non-commutative world, all of a sudden we have various generalizations, and then they are useful in different contexts. So first, and I'm putting this compact abelian just because this is the context of the talk, but this is true for any compact group, even for quantum groups, this proposition that, and this is your sanity check, because this notion of freeness, of saturated action of refill, it works so well with, let's say, cross products, for example, and the results of Morita type equivalence, that you want any definition you think of a principal bundle, like non-commutative quantum principal bundle, freeness has to be implied by this, and this is what we check. And this is a very nice, I called it a proposition here, but well, it's maybe in compact abelian case it's a proposition, but if you think about the full generality of compact quantum groups acting on C-star algebras, I would call it a theorem probably, and this is how we call it in the paper.
Mariusz, I'm confused. Don't we
Yep.
have a result that local triviality, that the finiteness of local triviality dimension implies a freeness in full generality?
Yes, we have. So this is somehow I was trying to be too, how to say, I said at the very beginning that I have compact abelian groups, and I put this assumption in all the results, not to focus attention, because but of course we have this in full generality, and I was trying to say that also.
Yeah,
Yeah.
because it's confusing. I mean, when you think that you
I
need to do
agree.
something,
I agree.
which you don't.
Yep. So you don't need this assumption. This is true for any compact group, and I don't want to go in quantum groups in this talk, but this is also true for compact quantum. Yep.
Yeah.
So so if we have now, and again, so for this proposition also, please ignore this abelian here. I was trying to be consistent in all the slides, but it's not really a good idea because it's confusing. So please ignore this abelian. For any compact group acting on the units of C-star algebra, we can prove that, okay, in general, they might be different, but dimension 0 is the same for all the different versions. Okay, and if we have, so the dimension, weak local triviality dimension is 0 if and only if the plane and the strong are 0. And if G is compact abelian, so now here I have G hat, so I need abelian. So I look at Pontryagin dual. Then it also implies, and it's equivalent to the fact that A is a cross product with the fixed point algebra by the dual action. Okay, and this is something that is connected to a Landstadt theorem. So we know that, so somehow this also tells you that trivial bundles, and this is, I think it's maybe good to emphasize, is that trivial bundles are like cross products. So in topology, trivial bundles come from Cartesian product of the space and the group, right? These are trivial bundles. But in non-commutative topology, tensor products generalize Cartesian products, but somehow this is too restrictive because in tensor algebras, there's a lot of commutativity involved. So to remedy this, and I think, and also examples, and this definition in particular shows you that what you actually want is a cross product. So let me also mention, so the dimension 0, what does that mean? It means that we have just one map from the cone of G to A. And then either this element is invertible, or this is or it's 1. So even in this invertible case, you can prove that having an equivariant map from the cone is equivalent to having an equivariant map from C0 of G to A. And this is generalizing the fact from classical topology, when we know that the principal bundle is trivial if there exists an equivariant map from the total space to the group, right? So the triviality, the trivial local triviality dimension is just telling you this. And this notion of a trivial bundle was known before, and people were considering this notion before. So triviality as having a equivariant map from C0 of G to A. Okay, so we also recovered that with this definition. Okay, so I want to go now to very particular groups, because those are the groups that I want to talk more in what follows, because we're going to look at graph C-star algebras, and there. So this will be our playground for this definition and how it works and how it behaves in different examples. So we want to look at graph C-star algebras and gauge actions, which I'll mention in a second. But first, let me show you that in the case when you look at those very specific groups, we have very concrete conditions that you have to check to show that you have finite, weak, or plain or strong local triviality dimension. This is very very concrete. So what you have to do is, if your group is just U1, so complex numbers of norm 1, then of course the dual group is the integers. So your grading is by integers, and what you want to find normal elements in A1, right? So the A1 here. So this is not the fixed point algebra, right? This is this first, because now our grading is by Z, so the trivial element is 0. So we want to look at elements in the first spectral subspace, and we ask them to be normal, and normality is of course forced on us because we want to look at maps from C0 of U1, and this is generated by one unitary, right? So the image of that unitary of this element T's tensor U has to be normal. So this is basically how you prove this, that you need normal elements. And you look at AI star and you sum them up, and if this is invertible, then your algebra has weak local triviality dimension less or equal to n. If this adds up to 1, then it's plain. And if those elements pairwise commute and add up to 1, this is the strong local triviality dimension. Okay, this is for a specific group U1. And for its finite subgroups, first let me add this notation that what this part of the talk is about is this notation of the star k. So for a finite group Z mod kz, it's self-dual, right? I wanted to write down here, so there's typo. So the dual of this group is again Z mod k, right? This is a finite group. It's a self-dual. So
Mariusz, let me jump in. While it is clear why 3 does not imply 2, okay? I mean, that you have stronger assumptions in 3 than in 2. Sorry, it's clear why 2 does not imply 3, because we have an additional assumption of commutativity. It is not immediately obvious that 1 does not imply 2. And here the reason is that you'd like to normalize it by the inverse. You would screw up the conditions that these A's are in A1, right?
Oh yes, right. Yeah,
So
thank you.
that's the
Yeah,
reason
because this
why
is
you
not
cannot just
immediate. Yep.
normalize it, and why indeed 2 is in non-commutative examples very easily something stronger than 1. Okay.
Yep. Yep. Yeah. Thanks.
And I like the notation star k, stark.
Yeah. That wasn't intentional, but yeah. Okay. So now here we not only want to have normal elements, So for if your group is U1, you just want normal elements. And here we have normal elements plus something more. So their spectra have to be in this set star K, where K is just the order of the group. And so we need additional assumptions of those elements. And then do I write it down? Oh, for example, this means that for the 2-element group, for Z2, these elements have to be self-adjoint. So then if you look, and we spend a lot of time, because that's the easiest possible group to act with, we spend a lot of time on actions of Z2 on various examples. And then you just need to find some self-adjoint elements that satisfies conditions 1, 2, or 3. Let's see. So okay, now I'll just for notation that this definition. This is the main definition of the project, of course, of graph C-star algebra. But so that you see what notation I'm using, let me just quickly mention that I'm using the notation. Yeah, oh, here you can see which convention. Sorry, which convention I'm using. So it's not the Australian convention. But now it's kind of varies, but it's I know that in higher rank graphs, in topological graphs, topological quivers, now even in topology, so this is a thing that, well, you always have to make sure that you know which convention you're using. So even in topological quivers, there are people that use different conventions. But let me not go into that anymore. So by a graph, I mean this quadruple. I have the vertex set, the edge set, and the range and source. And for me, I just want finite graphs, so that then the definition is easy, because all the interesting examples that we looked at and that come from non-commutative topology and Q deformations of spaces, usually we have finite graphs. So
well, I beg to differ. I mean, just take Podley sphere and projective spaces and.
oh yes, okay. But the examples I'll be talking about will be finite graphs. Yeah, I should have mentioned that. So, and this is the definition of a graph C-star algebra, which everyone knows for sure. Let me only mention some things that will be needed for me. So for finite graphs, this is always unital. It's implied by the fact that the edge set, that the vertex set is fine, right? Because the unit is the sum of all vertex projections. Now, many C-star algebras arise that way: matrix algebras, Kunz algebras, Tobolski algebras, Q-deform spheres, Q-deform length spaces, and many more. Let me mention that in this, in this part B of our application, we specifically mentioned that we wanted to look at Kunz algebras, Tobolski algebras, Q-deform spheres, and Q-deform length spaces. I'm going to report and talk about matrix algebras, Kunz algebras, Tobolski algebras, and spheres. There's not much progress when it comes to Q-deform length spaces. And so this is something to, and because already classically length spaces, they have a difficult, the local trivialization is not as easy as in, let's say, for spheres. Okay, let's look at the and now also the gauge action. So this will be our examples would be, we look at graph C-star algebras and we equip them with an action of a abelian compact group, and this is the well-known gauge action. And we want to look at which the graph C-star algebras, when you look at them as G C-star algebras with or U1 C-star algebras, when U1 is when your action is the gauge action, which of them are locally trivial or as principal bundles, or can we even talk about principal bundles? I want to maybe stop for a second here, that of course you could look at different actions of graph C-star algebras. For example, there are papers, I think this is Kumjian and Pask, when they looked at actions of groups on graphs, where the action on the graph is by graph automorphisms, right? Which the gauge action is not of this type. So if you look at the graph automorphisms, it induces an action on the C-star algebra. And then the question would be which of those actions are locally trivial actions. However, here why we're looking at gauge actions and not at those other actions, which might be very interesting also, is that there is a theorem that if you have a free action of a finite group on a finite graph, then it has to be of this very particular form of a derived graph or something called a skew product graph. So and you can prove, and this was proved by Kumjian and Paz, that if you have a skew product graph, then this is isomorphic to a cross product C-star algebra. So it's trivial. So this the bundle is trivial. So whenever the action is free, it's automatically trivial. So that's why it's maybe more interesting to look at gauge actions and not actions coming from graph automorphisms. And this theorem I mentioned is by Gross and Tucker. This is a theorem in graph theory, that if you have a finite group acting on a finite graph and this action is free, however, this action is both source and range map has to be equivariant now. So this is very different. So if you have a free action of a group on a graph, it kind of makes your graph very symmetric. And that's why it's immediately of this type of a skew product. And that's why as a principal bundle, it's trivial. Okay, but back to gauge actions. But I wanted to talk about this because this is something different. And maybe in some other contexts of the higher rank graphs or groupoids, we would get something more interesting. And this is something that I'm working on. So I visited Arizona State University, and we were talking about graphs, groupoids, and topological graphs or topological quivers, where there is a chance, because so finite graphs, the topology is trivial, but when you look at topological graphs, there's a chance that those actions on graphs by graph automorphisms might give you something not necessarily trivial, but maybe locally trivial. And this is a work in progress. That is part of this project. Okay, so of course, we're going to obtain the gauge action by finite subgroups of U1, but just by restricting. And okay, so let me maybe mention first. So we want to look at finite local triviality dimensions, but I just showed you that finite local triviality dimension implies freeness. And freeness is the same as strong grading. So you have to first identify when the gauge action is free. And we were working on this. I remember some time ago, we talked about this with Piotr and with Soren. And we discovered some conditions. And we also talked about with Alex Kirpasito about this, who's also like, I'm mentioning people that are part of the network. And so we talked about this, and we found conditions. However, then Alex found a paper where someone already proved those conditions in the algebraic setting. So this is a result by Clark, Hazard, and Rigby, with Hazard being also the part, well, maybe hopefully a part of the network soon. I don't know what's the status.
He already is. I mean,
he already is. Great.
As of 12th of December, the EU has signed the amendment, so Hazrat passed the point of no return. He is now part of the game. And this is what I was explaining yesterday, that something similar happened to us, you and I, with the Katsura conditions. I mean,
that's true. Yeah.
We discovered them during the pandemic, and we're very happy about it. And then it turned out that a few years earlier, somebody did it in bigger generality. But let me reiterate, even if I said it yesterday, that a beautiful way to phrase target budgectivity condition was because of you going to Arizona and talking to John Quick. So this shows how such exchanges are really helpful in research. Yeah, I mean, this phrasing of conceptual phrasing of target budgectivity condition as a pullback, and it found its way immediately into the paper, which is now being published. So this is how helpful the network is. Yeah. Go ahead. Sorry for being interrupted.
Exactly. Sure.
Ali has a question. Sorry.
Oh, please.
Okay, I'm sorry to interrupt your talk. You introduced an action of U1 on every graph CSR algebra. On the other hand, you told that matrix algebra or Kunz algebra they can be realized as a graph CSR algebra. Is it trivial to ask the question that what is the precise graph whose graph algebra is the matrix algebra, and I'm curious, what is the action of U1 on the corresponding graph? In fact, my question is that what is a graph whose algebra is matrix algebra, and how this action can be read on the on this graph, the U1 action?
Yeah, sure. So there's a explicit. You can explicitly write. So matrix algebra is the graph of a matrix algebra is just a line of length. If you look at matrices n by n matrices, that would be a line of length n-1, right? So oh yes, thank you.
Now these are 3 by 3 matrices.
Yes.
Okay.
So that's how the graph looks like, and our action is now. So it's not visible on the graph itself. It's only on the C-star algebra, right? Because so this action the gauge action comes from the fact that you can grade your algebra by lengths of paths, right? So the question is that so the action on those elements on the isometry, partial isometries corresponding to edges, this is just rephased, right, by this, like Piotr writes here. Just you multiply by lambda, and then you do nothing to.
My apology, I didn't understand yet what is the precise graph. My apology if the question is elementary. What is the graph whose algebra is matrix? Then I try to understand the action.
But we just answered your question. What is the graph?
So the graph is you just have a path of length n-1, and that's n by n matrices over C, over complex numbers.
Yes.
And then on this, if you look at the graph itself, the gauge action is not visible on the graph. It's visible on the algebra of the graph. Mm-hmm. I mentioned that you can have actions, of course, on graphs, and then by graph automorphisms. And for example, if you take a cycle graph, right, Cn, you can act by Zn on this by just by moving the cyclically the vertices in arrows, right? But this is not an action, a type of an action that I'm talking about. I'm talking about the gauge action, and it's on the level of C-star algebra. It's visible, and it comes from the fact that you can look at comes from the grading of this algebra by lengths of paths.
Mm-hmm. Yes,
and Bram was using a more sophisticated version. He would have a different unitary number acting on each of his isometries. This is what it was in Bram's talk.
Oh, okay. Yes. So of course, yeah. Okay. So let me so these are the conditions to have reactions. But let me maybe tell you about the context. So the result of Clark, Hazard, and Rigby is the following. So it's the result is that you look at groupoids. So they're looking at groupoids, and very particular. So they were looking at ample groupoids, because then you have the groupoid C-star algebra has a algebraic dense subalgebra called the Steinberg algebra, and they were looking at this notion of a strong grading. Right. So, and then they showed that this groupoid, the Steinberg algebra, is strongly graded by, again, so because this is if and only if the groupoid itself is strongly graded. And there's a notion of a grading of a groupoid. In the case of a graph, it's the usual grading by lengths of paths. And then they proved this result about strong grading. And then if you know that freeness is the same as strong grading, you can now translate this result and talk about graph algebras and finiteness of and freeness and strong grading of this algebra. And these are the conditions that, first of all, you have no this. Oh, you have no sinks. I think this is just saying you that you have no sinks, written in a very convoluted way. But so the preimage of a source map for any element is non-empty. And then there's this more technical condition. I'm not going to maybe talk about it too much, but this is just a technical condition so that you know that the gauge action is free. For the Z2 action, we have a simpler condition that every sink receives a path of length k minus 1. Okay, and now, so this is so whatever, if you're trying to look at dimensions, local triviality dimensions, you have to first look at this class of graphs, because what is nice about this about graph C-star algebras in general, of course, is that a lot of properties of the algebra, even the action, can be written in terms of graphs themselves. So these two conditions. Yeah.
Can I make a comment? I think that the second condition only matters when the graph is not finite. If it is finite, then no sink is enough to have, because by free action you just mean strong grading, right?
Yes.
Yeah, so for a finite graph, the first condition is necessary and sufficient. You don't need the second.
That's true. I will even mention this. Yes, thank you. But however, wait a second, but infinite, forever infinite. Oh, so you're saying that this condition 2 is not needed if your graph is finite, but
it's automatic. You can show that it's
Oh,
automatic for a finite
okay.
graph. It is only it follows from the no sink condition. Is in one of the paper of these three guys. I don't remember which one, but
okay, yeah,
it's the one that usually I cite because I always work with finite graph, so which is easier. Okay.
Yeah, sure. Thank you. So yeah, again, I was trying to be consistent, and that's so of course this result is true for any graph. I already told you that this is true for in a much more general case of ample groupoids, and groupoid of a graph is an example of an ample groupoid. So
Okay.
yes, I'm sorry for this, but again, ignore finite here. And as Francesco said, thank you for that. If you add finite, then this condition 2 is not needed. Okay, thanks.
Okay. Go ahead with your question.
Thank you. I don't quite understand the second condition. Why can you not take beta to be the same as nu?
Because it says for every m.
Yeah, this is for every m.
Or it's equal. Well,
For every m. So if you take the same, then you would have 0.
that's correct. Yes. But okay, now I understand. Thank you.
Sure.
Okay. Thanks a lot for clarification, Piotr. And let me go further. So now maybe some results. Yes. So the results are as follows. So we're looking first at finite acyclic graphs, so no loops, and this C-star algebra is now finite dimensional. And so for example of that is this matrix graph of a matrix algebra, just a finite path of length k. And then first of all, for finite acyclic graphs, the gauge action is not free. Right? If you look at because we always have we have to have sinks. This is basically the right, because if we have a cyclic graph and it's finite, it has to have a sink. There's no other way. And you can, of course, prove that, but this is also I think this is very believable. Right now, the result is as follows. So for finite acyclic graphs, we have this nice condition that freeness of the Z mod KZ action is equivalent of finiteness of the weak local triviality dimension. All right. So of course you cannot look at full U1. This, as I already told you, is not free. So we have to look at finite subgraphs of U1, and then freeness is equivalent to finiteness of one of those dimensions, right? Which I think is a nice result. And this shows you that the weak local triviality is good for finite acyclic graphs.
Mariusz, if you allow me to have a quick comment. because this is a very interesting property. And when you look at finite and cyclic graphs, well, except perhaps from matrix algebras, it's not quite clear geometrically what you are talking about. But if you take the Teplitz graph, okay, so this is the a graph of the Teplitz C-star algebra, so quantum disk. Again, you can prove that the gauge action here is not free. And geometrically, you should expect it not to be free because there is no free finite, non-trivial finite group action of classical disk. So why should it exist on a quantum disk? However, you have exactly the same effect that when you restrict the gauge action to any cyclic subgroup, okay, then this action on a quantum disk is free, unlike in its classical counterpart. And this is a very interesting geometric effect, that the gauge action itself is not free, but its restriction to a cyclic subgroup is free. And if you want, it's a very interesting quantum effect. Sorry for the interruption, but I thought.
Yeah, please. No, this is important. So also, how much time do I have?
You have -6 minutes.
Oh, shoot. Oh, cool. Okay, let's go. Now, so first, let me just mention quickly the results, okay, and then I'll finish. So matrix algebras, this is 0 or infinity, looking at depending on whether k divides n, right? So if k divides n, then you can prove that then the dimensions agree, and you can look at your matrix algebra as a cross product. But if they don't agree, you can prove that already the local triviality and the strong local triviality is infinite. However, the weak local triviality is finite, right? So again, this is showing you that for those finite acyclic graphs, weak local triviality is the good notion, but strong and plain local triviality is not too useful at 0 or infinity. Okay, so now if we talk about the n-cycle graph, I already mentioned the n-cycle graph. It's just a cycle of length n, and then we can prove that the C-star algebra of this graph is matrices over functions on the circle, right? So then we have the following possibilities. Either, and here this is interesting. First of all, we have results that if you have an equivariant maps between two C-star algebras, then the dimension of the codomain of that map has to, so the algebra in the codomain has to be smaller or equal than the dimension of the algebra in the domain. And here we have a map from C of S1 to matrices over C of S1. And now we know that the dimension of this guy with the action of Z mod K is always is less or equal 1, right? It's even equal 1. So that's why we know that it cannot be 0 infinity like for matrices. It has to be 0 or 1. And in fact, here all the local triviality dimensions are either 0 or 1. Okay, so Kuhn's algebra, first, the full gauge action is infinity. And this is very interesting quantum effect, because in classical theory, if you have a compact connected Lie group acting on a locally compact space, then by Palais result, if your action is free and proper, and if your group is compact, then the action is automatically proper, then this is locally trivial. But in the non-commutative case, this is not necessarily true, because we have an action of a compact Lie group that is free, because you can prove that the gauge action on the Kuhn's algebra is free. It satisfies the conditions that I mentioned here, but its weak local triviality dimension is infinite. So if you look at the dimension at finite subgroups, then we have some more results, both for weak and for local triviality. And sometimes they're for the Z2 action, it's even we have a bound for the dimension, the plane dimension. Now for the Teplitz algebra, this is something that Piotr mentioned, that the full action is not free, but the dimension of the two-element group, the two-element subgroup, is exactly 1, which is, so this is interesting because so on one hand we have this, but then the strong local triviality dimension is infinite. And here we use KK theory and mainly K homology to prove this result. And we were able to use any sort of K theoretical methods only because there's a strong local triviality dimension. So let me maybe at the very last mention that to find those dimensions, unfortunately, K theory or KK theory is not so useful most of the time. And this is related to some fundamental results that we have on the fact that finiteness of the local triviality dimension is related to maps from free joins, whatever that is. So classically, local finiteness, we have this classifying space, and every local trivial principal bundle has a G-equivariant map into that classifying space. So in the quantum realm, when you talk about dimensions and this local triviality dimension, your classifying spaces are we have an analog of this, and these are the free joins. However, K-theoretical data of those free joins is trivial. So there's nothing interesting. So you cannot use that to compute the dimensions. However, in the strong local triviality dimension case, you can use it, and we were able to use it to prove that the strong dimension is infinite, even though for, let's say, Z2, it's 1, the weak local triviality dimension is 1. So you see already here examples where one of the dimensions is interesting and the other one is not so useful. And for quantum spheres, we have the same exact results like classically. We only look at Z2 because this is the antipodal action. And I guess I'm going to finish here because I'm already out of time. And let me only mention that the examples I'm talking about here were mentioned in the project application. So both the Kunz algebras, the Tobolski algebras, and the quantum spheres. However, the quantum length spaces, this is not clear to us how this will work. And also, there's a work in progress to find some examples of that in the world of topological graphs and topological quivers. And this is also in a project I started with when I visited Arizona. I visited their Jack Spielberg and John Quigg, which are part of the network. And I talked to PhD students there at Arizona, and we have this project which in which we hope to find some new examples of locally trivial actions of groups on C-star algebras of some sort of graphs. What is also work in progress and was also mentioned in our applications that for higher rank graphs we don't know much. So this is also open. So anyone interested in this that is part of the network can look at those type of problems. They're very concrete problems. We want to look at examples and find examples of let's say the gauge actions on higher rank graphs that are, we know when they are free because this is again groupoid of a higher rank graph is ample, so we know when they are free. Then now the question is when they have finite local triviality dimensions. And I'll stop here. Thank you very much.
Yeah, thank you very much. Just let me ask you the timing question. All these results, the CPT results, have a date 21, and our project started in 23. So do we have any results actually achieved within the project?
Yeah, that's we have results achieved in the project. So I remember it was taking some time, right? Because we had several applications of this, and and then the results were coming in. But what we have for sure is that within the project, what we were able to do is, first of all, I have in my paper on non-commuted principal bundles that are not necessarily compact. right? So locally compact ones. I have examples that come from graph C-star algebras that I computed, and so we have results like that. And we also, those two projects that I started with in Arizona are also connected to this. Also, there's this notion of a non-commutative classifying space that we defined with Alex Kirvasi to Harvard. So this paper is not yet published, and it's taking a long time, but it's already submitted for publication, and I'm expecting the next two papers. So one is already published, and I'm expecting two new papers to be published next year with new results in this work package.
Okay, thank you very much. I'm very happy with your answer, and let me sort of finalize your presentation by making a comment which Ludwig should have made, because you have a beautiful joint work in the classical setting, and
oh, this I have something.
okay.
I have something.
Okay.
This is
Okay,
this
so
is
this is okay. Okay, all
yes.
right, yes, very good. Because this work. So let me put it very succinctly. Is related to a very famous problem. So first, it goes back to Hilbert's fifth problem. Then it's Hilbert-Smith problem, and this is like $1 million problem. It's on the level of a millennium problems in terms of difficulty. And you see, the conjecture that we made, which Mariusz highlights here, implies this Hilbert-Smith conjecture that it is true. And here the name of the game is precisely to see what happens when the local triviality dimension is not finite, you see, because we have things done classically when the local triviality dimension is finite. But the difficulty of Hilbert-Smith is that it concerns principal bundles that are compact but not locally trivial. And we want to prove the non-existence of a certain continuous equivariant map. And this implies the Hilbert-Smith conjecture, which is very, very, very famous. And it kind of motivates this working around. Of course, this is a working around the dimension, but I would like to emphasize, because when you listen to Mariusz, you have an impression that it's also easy peasy. No, in fact, these are difficult results. Computing these dimensions is typically, not always, but typically quite difficult, right, Mariusz? And,
yes, thank you.
And this is
because
why
I was
we're
going
sort of groping in darkness,
Yeah.
trying to find
Yeah.
anything which is computable.
Yeah, so I was just flashing those results very quickly, and then you might think, oh, but
Exactly.
like
Yeah.
already here, I was trying to emphasize that already here you had to use some sophisticated machinery to even get an answer. And
Exactly.
for example, oh, here, this is always a good problem for anyone thinking that this is easy. What about local triviality dimension, plain local triviality dimension of Z2 with the templates? So find two self-adjoint elements that are odd in the templates algebra and add up to 1.
Yeah.
It's a very difficult problem.
Yeah, even Voronovich completely failed when trying to help us solve it. Yes. Yes. Okay.
However, so yeah, my experience is whenever I tell someone to compute this, then everyone's like, oh, this should be very easy. And then it turns out it's not.
Exactly. Okay, Mariusz, thank you very much.